Division algorithm. Division algorithm is actually a really strong algorithm, but people do not realize how strong it could be. A lot of time you can use it to show that an equation has no integer solutions. So like this, something like this. So this is what you've seen in class before, which I did it in my last tutorial. The 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 video will be uploaded after this because I've been teaching for the whole morning. Didn't have time to upload the video, but it will be uploaded after we're done with this. Okay, so what does it tell us? It tells us for all, if you have natural numbers a, b, then there is a unique pair of integers q and r, where q is a quotient, r is a remainder, with q is greater than or equal to 0. So this is greater than or equal to 0. R is in between 0 and b. So R can be 0, 1, all the way to b. Okay, so a few hints for you is when you deal with something like this, you do not want fractions. So when you do something like this, you don't want fractions, you only want integers because you are dealing with integer solutions. So in divisibility chapter, remember, we always want integers. So if in your proof somewhere it appeared something like a fraction or logarithm, something like that, you always want to get rid of it and get back to integer. Okay, so remember what I said, because you should always take away those tips or techniques, concepts behind the question instead of just memorizing the solution, which a lot of you are doing that, which is really bad. So again, I'm mentioning it again. In this chapter, we're dealing with divisibility. So we're talking about integers. So whenever your proof it's not an integer, you always want to try something to get back to integer. So it's going to be easier for you. Another thing is we use remainder a lot. This is quite important. So for example, using this as an example, you know that, oh, you want to divide by 3, and in other cases like the example you did in class, it was like 5 times something. So divided by 5, you know the remainder could be 0, 1, 2, 3, 4, and so on. So those are something that's really helpful. And another thing that's really helpful is even and odd. A lot of time you can just discuss the parity of the questions and reach a contradiction somewhere like that. So let me use an example to show you what I meant by that. We will do this question. So move on to this page. So page 5. Let's try example 3. Let's do this one. This one is not the same as the other one. Sorry. Sorry that I hurt your eyes. I know you guys hate light mode. I apologize. Alright, so look at this. What can we do? Prove that this has no integer solution, where x is greater than 1. What can we do with this? Any idea, any suggestion? This question is on problem set J, is it? I didn't know. Did they give you a solution? Yes? Ah! I hate this! Okay, then skip this. Then I'm not gonna do it. If you have a solution, then never mind. I hate when they give you a solution. I actually don't remember where I got it from. You have a solution already, so what's the point of me going over this? Skip that, let's talk about GCD then. It's the same. Just read the solution and understand from there. GCD. GCD is the greatest common divisor if we have a and b be two integers, not both zero, then the greatest common divisor is the largest integer that divides both numbers. So remember, it's the largest. The largest. That is why GCD 08 equals to 8, because, well, 0 is 0 has lots of divisors, but in this case, the biggest one is 8. It's not 0, okay? It's not 0. So the smallest GCD you can have is gonna be 1. Let me have a look at their solution. If you want me to go over, I wanna see if their solution is the same as my solution. If it is, then I don't wanna do it. If it's not, then we can do it. Which question is it? Problem set J. 2? Okay, let me see. Let me check their solution. J. Where is the solution? 2. The solution is pretty good already. Yeah, I'm not gonna do it. There is a solution that I really don't like though. The solution for 4.6.32 is horrible. Oh, I'm recording. I should not say that. Sorry. It's not horrible, but I don't like it. I really don't like the solution for 5.6.32. Don't know who wrote that, but it's a horrible solution. No. Ugh. I'll show you my solution later, but let's continue. I think for this question, the solution is pretty good, so I'm not gonna do it. This one, I'm not gonna do it. The three, this one, not gonna do it. But the other one, the one I said I don't like your solution, we can do that one. Okay, GCD. We talk about GCD, and this one is very useful, very useful. When you petition to change lectures to 1 hour and tutorials to 3 hours. If you change my tutorial to 3 hours, I don't even know what to do. I don't even know what I'm gonna do. It's pretty much like, I don't know. But yeah, um, this one is really useful. So let me find a question that to show you it is useful, because otherwise you are not gonna believe me. It's useful. I know you. Do you believe me? But let's do something. I don't even know. I don't even know what I want to do. Okay. I actually don't know what I want to do. Let me see what you have. So, um, so something like, so you know the GCD, they can give you something like, let me just pick something random. I don't know, like 24, and add some I want to add some variables to it. Let me think. Oh, what about this one? It might not be, well, it might not be using this, but what about this one? GCD of 10 factorial and b equals to, no, 10 factorial and 2 to the power of 10. Compute this. What is this? Are you sure? Ten factorial is 10 times 9 times 8 times. Yeah, someone wrote it already. That's 10 factorial. So if they ask you what is the GCD of those two, what are you gonna do? Factorization is a good idea. How do we do that? It is prime factorization if you're thinking in that way, you're on the right track. How did you get to the power of 8? It is correct, but how did you get there? Rewrite 10 factorial. Okay, 10 factorial equals to what? Someone tell me, how do you write it? So it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 2 times 1, which equals to 2 to the power of what? So this is 2. This has 1, 2, so this is 2 times 5. This is 3 squared. This is 2 to the power of 3. 7 is 7. This is 2 times 3. This is 2 times 2. So how many 2's do we have? Missed 3. Yeah, I did. So my bad. How many 2's do we have? 8. Okay, so this is 2 to the power of 8 times 3 to the power of what? 3 to the power of 4. Let me double check. 1, 2, 3, 4. Yeah. Anything else? Times 5 to the power of what? 2 times 7. 7 to the power of 1. So this is 10 factorial. The other one is 2 to the power of 10. So what is so looking at this and this, what is GCD? 2 to the power of 8. Okay. So this is 2 to the power of 8. So this is telling you that, well, you don't necessarily need to use Euclidean algorithm. Sometimes the GCD is more helpful. What else do I want to do? Let me think. GCD. I think that's it. That's all I want to do. Let's do example 2. So find with proof all integer x satisfy x equals to GCD 25 and 5x plus 4. How do I do this? How is it the greatest common divisor? Because their common divisors could be 2. Only common divisors are 2 to the power of something, and 2 to the 8 is the biggest one. That's why. All the other ones are not common divisors. Does that make sense? Example 2, how do we approach this question? Someone tell me, how do we approach this? 25 equal to 5x plus 4? Why equal? Why are they equal? You cannot just let them equal. GCD this minus 5x plus 4 minus 2 times 2, y minus 2 times 2. No, not shouldn't x be 1, y is a 1. Also, with proof, all integer x. So you need to, if you think 1 works, why does other integer not work? Okay, yeah, that is correct. That is correct. That's great. You're on the right track. Okay, it's because, so proof. It's because what? Because the GCD x equals to GCD of 25, 5x plus 4. Then x should divide 25. Do we agree with that? Do we agree with x must divide 25? And it must be smaller or equal to 25 as well, right? Do we agree with that? Right. What does this mean? This means that it can only be divisors of 25. So x can only be divisors of 25. So it can be 1, 5, or 25. So 25 divides itself. Or why should x divides? Because x is the common divisor of those two. If it's a common divisor, then it's a divisor of 25, right? Does that make sense? So you should know that GCD of AB divides A and GCD of AB divides B. This is by definition. So we know that it's either 1, 5, or 25. Now you can just discuss cases. If x equals to 1, then we have GCD 25 and 5 plus 4. Okay, what is this? This is GCD of 25, 9, which equals to 1. So this is okay. So 1 is one of our solution. If x is 5, what do we have? Then GCD of 25, so that's 10 plus 4, is GCD 25, 14. What's the GCD of those two numbers? Oh wait, 5 times 5, it's not 14, sorry, my bad. It's 25 plus 4, it's 29. What is the GCD of those two numbers? 1. But x is 5, so it's not 5. You see? So 5 is not a solution. If x equals to 25, then GCD 25, and then 5 times 25 is 125 plus 4 is 129. Sorry, I should show all my work. Otherwise, if you don't show your work, we might deduct more from you. Don't cry if they deduct more from you. What is this? What is the GCD of this? Anyone? 1? Which is also not 25. So what does this tell us? What is my solution? 1, right? So therefore, the only x that the only integer that satisfies equals to GCD 25 by x plus 4 is 1. Okay, do we have any question for this one? What if it was 3 instead of 5? Which one do you want to change it to 3? Like here, 5x changed to 3x? Is that what you mean? 9 3x plus 4. Oh, it's the same. It's the same. It's the same. So you need to discuss divisors of 9 and discuss cases. So it's gonna be 1, 3, 9. Plug them in and see if you can get anything. Does that make sense? Do we have questions? Why does x have to be positive? Because it's a GCD. Remember GCD? The smallest one? The smallest one is 1, remember? Yeah, the smallest GCD is 1. If you're given a very large number, if they give you a really large number, then it's definitely gonna be with very little factors. What is GCD 0, 0? Let A and B be two integers, not both 0. Do you see? Not both 0. Half of you were also in the last tutorial. I want to see if there is another question I want to do. What was the question again? Can someone send me the picture of the question? The specific question. It was something like union of some countable. Oh, I think it says A and B are disjoint countable sets. Have to prove that A union B is also countable. Right? Is this the question? Yeah, I did this in office hours. I didn't do it I didn't do it in tutorial, but I did it in office hours. This one. I do not like their solution because it's really hard to understand, to be honest. So basically the idea is the following. A is countable. So A is countable. Since A, B are disjoint and countable, that means you can list it out. We can write A as A1, A2, A3, and A1, B2, B3, and so on. Okay, because you're countable means you're listable. Yeah, I don't know what's wrong with my Siri. Just when I call her, she doesn't answer. When I don't call her, she's like, "What's up? I'm here," and I'm like, "Go away." Anyway, so because they are disjoint, you know that well, AI doesn't equal to BJ for any I and J. So the union, A union B would just be A1, B1, A2, B2, and so on. Okay. So now what we want to do, I'm going to use another color. What we want to do is I want to have a bijection between natural number and A union B. So natural numbers are 1, 2, 3, 4, 5, 6, 7, and so on. A union B is A1, B1, A2, B2, A3, B3. Ah, shut up! No. And so on. Okay, and now we want to map A1 to A1, 2 to B1, 3 to A2, 4 to B2, 5 to A3, 6 to B3, 7 to A4, and so on. So this is a function I have, but I want to use the arrow diagram because arrow diagram is not a formal proof. So we want to come up with a formal proof, right? We want to come up with a formal proof. So what do? I want to map this to this, this to this, this to this. So what I know is, since A is countable, there exists a bijection F mapping from natural number to A. Okay, and what is the mapping? So let's draw the mapping. The mapping is 1 to A1, 2 to A2, 3 to A3, and so on, 4 to A4, and so on. Okay, and B is countable as well. So we have another bijection. C. Oh, I should write the actual thing. So the bijection is F of N equals to AN. And G is from natural to B, and the mapping is F of N equals to Bn. Okay, so the mapping is basically what I have. So 1 to A1, 2 to A2, 3 to A3, 4 to A4, and so on. This is 1 to B1, 2 to B2, 3 to B3, and so on. So I have those two functions. I want to use those two. Oops, this is not F, this is C. I want to use those two functions to come up with a new function such that 1 is to A1, 2 is to B1. So by looking at this, I notice that all the even ones and odd ones are together. You see, the odd ones map to A's, even ones map to B's. Do you guys see that? Do you see the pattern? So that means we need a piecewise function. So let's define mapping from natural number to A union B. And how do we map it? H of x equals to something when x is, let's say, odd. So what is the function I need? I want 1 to A1, 3 to A2, 5 to A3. What is the function? If the sets are not disjoint, then you need to remove the intersection part and do the same thing. I will talk about it later once we figure it out. So how do I do this? How do I map this to this using f? Because f is from natural number to a's. So it's f of something. So remember, it's 1 to 1, 3 to 2, 5 to 3. How do you map? Because before it's n to n, now you need to n to, not n anymore, but something else. X plus 1 over 2, that's correct. So it's f of x plus 1 over 2. You see? Does that make sense? Because, well, you want 3 to 2, 5 to 3, plus 1 over 2 is 3, plus 1 over 2 is 2, and so on. Yes, and g is x over 2 for even. G of x over 2. When x is even. Now you need to quickly show it's a bijection and then proof. This you can do it yourself. When you do it, remember your f and g are bijective already. So back to one of you asked me, what if it's not disjoint? So, oh, let's do B first and then we'll go over that. When the solution takes longer than the solution that shows it's just listable, because you say it's just listable, it's not really a formal proof. Yeah, it's informal. This is not a composition though. So 102 before would say you can finish here. You don't even need this. Before 102 would say, oh, you draw the arrow diagram, and this you can just say, oh, this is a bijection. Done. But now we do not accept it anymore, so you need an explicit function. Or a professor said specifically we do not accept arrow diagrams on Piazza, so it's not accepted anymore. So we need to come up with a specific example. Okay. He says use this to show, use part A to show that irrational numbers is numbers. The set of irrational numbers, sorry, my bad. Is uncountable. Okay. How do we show that? Notice that note that irrational number is what? Is real number irrational. How do we show it's bijective? You prove it's injective and surjective by discussing cases. We did many of the piecewise functions showing it's injective and surjective already, so I don't want to do it anymore. Okay, but we did so many. This is basically R minus Q, where R is real number, Q is a rational number. So for contradiction, let's suppose it's countable. Right, suppose it's countable. We know that. We know Q is countable. We know this. And Q, R minus Q is irrational. Intercept Q is empty set. So this means they are both countable and disjoint. Done by part A, Q union R minus Q, which is R, is also countable. And this is a contradiction because we know R is not countable. Okay, R is not countable. Does this make sense to you? I'm not sure if this makes sense to you. So let me know what do you think, if it makes sense to you. Makes sense. Okay, so back to someone asked me, what if A and B are not disjoint? Here, what if A and B are not disjoint? What do we do if they are not disjoint? You, if they are not disjoint, then you need to write one of them as a disjoint set. So A union B can be rewritten as A union B minus A. Okay? You need to prove this. Okay? Now A and B minus A are disjoint. So you just need to prove the union of those two is countable using the same method as before. That's all you need to do. Okay? Does this make sense? Set identities are not bad. They are not bad. They really are not bad. Okay, I think